other orbitals, it decreases. So it means that we have like electromolecular density transfer from neighbor to those elements. And to prove also, we use the matter charge calculation by PFD, and we observe yes, the same result, that we have a kind of charge density distribution change on our surface. Okay, the next experiment is Raman spectroscopy to see that if we have any metallic phase or not. And actually, we didn't need any metallic phase because we need a uniform. And as you can see, the Raman spectra, MOS2, QMOS2, and others, is almost the same peak of MOS2. We have just some peaks related to the vanadium sulfide vibrational modes. And the sample is quite uniform. When we grow the sample, we always check the 10 different points of the sample to be sure about this. And the next experiment is the U-visible spectra of monolayer sample. For this, we need to transfer our sample on a transparent substrate and measure its absorbance. And as you can see here, the two phenomena are here. First, the light absorption increased. It means that we have more light matter interaction. And also we have a kind of shift of the band gap to the lower energy or larger wave numbers. It means that we will have presumably a large amount of the mid-gap states. And more interesting, we observed that the photoluminescence of the MOS2 completely quenched. And this quenching is also interesting because it means that now we don't have any radiative recombination. All the pathway goes through the non-radiative recombination. So the most important thing from this slide for us is enhancement of the optical absorption if we count the xenon lamp as a spectrum, because we use the xenon lamp for our next experiment. And it's like 2 to 4%. It means that by the MOS we can absorb 4% of our light. It's quite high. I don't know that the quality is good. You can see, right? Everyone can see the. I don't know because. Okay. So the next experiment is studying the microstructure of our sample. It's very important. If we don't know the microstructure, we cannot provide any feedback to the theoretical guys to do the calculation. The first three, the up image is the MOS2 sample. You can get a lot of information from the STM images, like the grain size, grain boundaries, edge morphology, stacking orders. The second thing means that if you have bilayer, they can have different kind of stacking orders on top of each other, we call it like AA, AB, or they can also have being twisted on each other, at different degrees that you can see here. And we observe two different things when we have vanadium in our sample. The first one is that if you see here, we have some dark region, in some part of the sample. It means a kind of accumulation of the vanadium and vacancy together. It's matched already with what we observed from the theoretical calculation. And the second thing is the distortion. The lattice here is not exactly hexagonal once we have vanadium. Okay, when you put vanadium inside the lattice, and when you provide some vacancy, means take one of the elements there, all the interaction change, right? It means the lattice should be arranged to minimize the energy. For sure, we will have some distortion. It's not always, sometimes it's not visible, but for sure we could observe. And for me, it was a question that why we have this kind of dark region. Then I considered a kind of model based on the input from the DFT calculation. I wrote a code and considered the formation energy of the vanadium in the lattice of MOS2, and also vacancy in MOS2 with and without vanadium, and also considered modified them for scattering and for the brightness of each point, because when electron come and leave, it can scatter from any atoms, and this scattering is a function of the Z is the atomic number, the power of 1.7. I think everyone of you should know it from the undergrad quantum scattering, section of the quantum mechanics. So after considering this kind of things and provide the model structure and rotate them like this, like we have here, we could see again this kind of dark region. Although this one is perfect, this one is experiment, a bit different. Different should be here. So much. And the last a slide for the application is our target. Okay, now we make the material. Is it suitable for PCC2 reduction or not? And this is the experiment that we have done. As I told you, we have a chamber, CO2 gas, water vapor, shine the light, we get the, some other like product, by a syringe we get the product and inject to some gas chromatography system. And we can measure the product here. As you can see here, between the green one and the red one, we have like 5-time enhancement in the CO yield. Although it's like nanomole, right? I told you initially that we are too far from the industry. If if we breathe, we provide more like probably CO2. It means that the next generation should try more to push it to possibly micromole, few of the most. Anyway, we have this 5-time enhancement that is because of the presence of vanadium and sulfur vacancy. But one of you would ask me that it possibly due to the sulfur vacancy, not vanadium. So we provided 2 standard samples. Any experiment should have some a standard sample or some like distinguish the parameter from each other. And as you can see that yes, if we have sulfur vacancy, it can improve the efficiency as anyone knows. But once we have vanadium, it can boost it even more. So the reason behind this enhancement can be like a lot of reasons, right? We need to investigate them one by one. The first thing that we studied is the calculation of the binding energy of hydrogen and CO2 to the surface. If we have active site, it means they should also absorb the CO2 molecule very well, right? You can see here that if we increase the X value, yeah, we have a better absorption for water and even for the CO2 and also intermediate transition state. Yeah. The second thing is that do we have a better charge transfer? Charge transfer. These are different. Charge transfer means that in the 2D material, charge transfer between electron transfer, photon transfer between the material and your molecule. So I have done it with using the atomic force microscopy. How it's like a kind of AFM experiment in the liquid that we can measure the chemical performance of our material. As you can compare these two samples, the left one and the right one, you can see that a big enhancement for the right sample. Here. And it means that we have a better charge transfer or charge transfer in our sample. And the last experiment, possibly everyone is familiar in this building, is the UPS and UPS experiment to provide the band structure. I didn't provide the band structure because I suppose that everyone does know this effect. So we also observed that once we have another sort of vacancy, the conduction and the valence band of our sample perfectly sandwich the reduction level of CO2 and oxidation level of water. It means that if we have any excitation, whole can be injected to the water and electron can be injected to the CO2 to do the reduction process. So if our best result with the quantum efficiency of like 0.02% is disappointing. But if we compare with the literature, this is the work that we have done between the last 10 years in our group. We are not bad. We also, surpass a lot of research that we have done in our previous work. We have now the 2 examples of the film, like one is this one and another one is my previous work, 0.2 for WSC2. I always also write like this that we can. Whenever we go to present this work to any conference or anywhere, people say that your efficiency is very low. It's better to change your application. But we always remember 10 years ago when we were like here, we cannot see. So we believe that if we work a bit more, every year we have some enhancement. One day we can pass 1% and attempt towards the 10% efficiency. But it means that we still need to work much harder. Anyway, let me summarize here. Here I show you that we can have a method that can help to grow the MOS2 film under the SI2, thin SI2 layer. And that SI2 layer can be kind of membrane to pass the sulfur and hydrogen to the liquid under it to grow the perfect MOS2. Also, I show you that if you have vanadium and it's kind of element, alloy element, and vacancy there, they can help for the better CO2 absorption and even better performance. Okay, let me finish my talk with first, thank you for coming here, attending this my talk. I'm really happy to see the students here because the email told me that all the faculty members would be here. the level of presentation would be a bit like high. If you have any question, you can ask me. I didn't provide it mostly for the students. And also I should thank my colleagues, Professor Chen, they give me the space and a lot of the students to work on a lot of topics that I show you one of them, and also NSTC. Thank you so much.
Okay, thanks for the interesting talk by Qorbani. Anyone has a question? Can I answer a question?
Sure.
So, if you really want to commercialize this kind of technique, the bottleneck is the bottleneck only the company which should sell these devices, or we need to consider about like the cost of verification or something else?
Yeah, very good question. Yes, we should consider the application process is expensive, and no one accepts this one. And also we need to consider, if you have qualifications like 80%, people would say, okay, we can buy. But we said our since method, I mean, it is like expensive. And also the qualifications is very low. It's not interesting for the industry anymore now. Since that we are working on it to make it suitable for industry. First of all, I think that we should improve the efficiency of records. The next step, think about how to make it cheaper. I should tell you that we have also some powder sample. It's very easy, right? Just, I should not say that. Just cooking. I don't like to go that direction. They can just put the powder, get large amount, and put get some efficiency. But I myself does not want to go that direction because we don't have any control on the surface to see any do any theoretical calculation. Yeah. First, pushing this one, and then think about how to make it cheaper. Yeah. I think Taiwan is a good environment to grow to make a film. It's one of the reasons I think we are the only group in the world working on the film for the CO2 reduction.
Why? Because we have this.
We think that I think Taiwan industry is very like mature for team film and also a few layer film application. So it wants to work in this direction.
Following this question, I guess this kind of research should be supported by some kind of environmental policy, something like this, supported by the government. Do you really see a strong driven force from the from our government or from?
I think this part, the answer is quite tricky because it depends who you work with, him or her, right? And it's very difficult for me as a foreigner came to Taiwan to answer this question, but mostly local professors that they can have a convincing discussion, negotiation with the government, they will make this. But for me, it's quite difficult. My Mandarin is a bit not strong nowadays. it needs also to talk like it.
Yeah, thank you for this discussion. Any other question?
I'm curious about one of your slides, and you mentioned that you calculate the energy outcome for each point on the film. Can I know more detail about it?
This one or next one?
Yeah. In one of your slides, you mentioned that you're calculating the energy outcome of each point on the film. But it's not in the slide, maybe in the more earlier one.
Right? Deformation energy. Or absorption energy. This
No, more earlier.
do you have any more?
Yeah, probably. I just want to know how do you calculate the energy outcome.
Okay. This part actually is done by our theoretical collaborators, but also the model also we discuss a lot. The model is that if you want to do VFD, you consider kind of unit cell, right?
Yeah.
Depends on your computer, how much money you have, you can make it bigger or smaller, right? Then after that, you need to consider the different kind of elements there, boundary conditions, and also the function you want to use the hybrid function, or you want to use like a kind of PDE level, low level calculation. So then you can make a lattice and calculate the formation energy.
Yeah.
Then you will take one of the sulfur from this and again calculate the formation energy.
Oh, okay.
Then the difference means the formation energy of sulfur that you can see there.
Okay, I got it.
So that it should be negative, otherwise it's not the same.
Yeah.
You mean this one? Then you need the thickness, right? For the thickness, we use the ALD to grow the like. For each layer, actually, I should say that we put a lot of time to make it very flat. If it is not flat, it will not give you a good result. So this kind of growth actually started like for 5 years ago. Each student came for the project. But the first student worked on the MO2 to make a MO2. So she could grow 1.5 or 1 nanometer MO2. And the second student also wants to grow the vanadium oxide and then sodium fluoride. So step by step, because sometimes you make a very uniform thing by ALD at the middle position. Then go for this system. Yeah, if you like, if you have a little like fluctuation, the SI will be great and it will come out and not more. This makes it maybe a bit expensive in terms of the price and control.
Any question? Okay, if there's no more question, let's thank Dr. Qorbani again.